1 minute. So am I audible?
Yes, sir.
Okay. Your screen is visible now?
Yes, sir.
Okay. Now, so yesterday we discussed, once again briefly I will explain you. Okay. Okay. So based on the conductivity of materials, so we can classify the materials into 3 categories. So those are the metals, semiconductors, insulators. Okay, so the conductivity range, if conductivity is greater than 10 to the power of 4, Siemens per meter, those materials we will call it as conductors. Okay, all metals are behave like a conductors. And if conductivity is less than 10 to the power of minus 4 Siemens per meter, those will act as a insulator. Those materials will act as a insulators. Okay, so and the conductivity range is in between 10 to the power of minus 4 to 10 to the power of 4. Okay, those materials will considered as a semiconductors. So this is about the based on the what is that range of conductivity. So we can classify the materials. Okay, now coming to the based on the band theory of solids. Here. Okay, so based on the band theory of solids, so also we can classify the materials. What is the band theory of solids means? So if you will take every electron, so every atom contain some electrons. So in that there are some inside electrons will be there. That means electrons are rotating around the nucleus. Some electrons are inner orbits, some electrons are rotating in outer orbits. So those electrons rotating in outer side orbits means we will call it as valency electrons. Okay, so those whatever the depends on their energy state. So those energy, so electrons are combinedly form one energy state. Like suppose here 2 electrons will be there. So suppose 2 outermost electrons will be there means their energy will be E1 and E2, like that. Suppose 3 electrons will be there means their energy state is like that. Suppose n atoms are there, so in that so many free electrons are there. Those free electrons combinedly form some band of energy. Okay, so here that band of energy, suppose if you will take n equal 1, that is the inner cell. That band is inner band. So this is the this also inner band. Only what is the outermost valency band means, so n equal 3 here. Suppose I am taking the example here. So suppose silicon or germanium. Okay, so if you will take silicon or germanium, so n equal 3. So that is the outermost cell. So these outermost electrons of all atoms, those energy levels are combined to form like a band. Okay, those outermost valency electrons are combined to form like a band. This band we will call it as valency band. So these valency electrons are loosely bound to the nucleus. Because these are in outermost cell. That's why what happened, nucleus attraction on the, so these outermost electrons is very less. That's why if you give little energy also, so those electrons escape from the nucleus, and those electrons will move freely inside the atom. Okay, if escaping from the nucleus attraction, what happened, those electrons are freely moved inside the atom. So because of these free electrons, what happened, conduction will be takes place. Okay, so that's why these electrons we will call it as conducting electrons. These electrons energy band we will call it as, so conduction band. Understood? So what is the valency band means? So outermost electrons, all outermost electrons combinedly form like a band gap. Okay, like a band, energy band. Okay, these band we will call it as valency band. If you give little energy to this valency band electrons, what happens, they will escape from the nucleus force. That's why what happened, they will move freely inside the atoms. inside the atoms. Those electrons having some energy. So okay, so like that electrons we will call it as conduction electrons. Okay, if free electrons will be there, those free electrons we will also call it as conduction electrons. These electrons energy level, we will call it as conduction band. So this is the band theory of the solids. Okay, so that is the valency band and conduction band. Okay, now coming to the, so based on gap between the valency band and conduction band, materials are classified into here three types. Okay, those are the conductors, insulators and semiconductors. If band gap between the valency band and conduction band will be very high, very high means what happened? So it is for escaping electron from valency band to conduction band means it's take very high energy. That means here, so these valency electrons are strongly bond with nucleus. So for that means for getting the free, so those electrons will move from valency band to conduction band. We have to give so much of energy. These type of materials we will call it as insulators. Okay, if energy gap will be high, means what happened? So here, so for escaping the electrons from valency band to conduction band, we have to give so much of energy. Okay, so why here energy gap will be high means these electrons are strongly bond with the nucleus, in case of insulators. Now coming to the, in case of semiconductors, the energy band gap between the valency band and conduction band is very small. So that's value is 0 to 3 electron volts. Okay, so already I explained you, for silicon it will be 1.21 electron volts, for germanium 0.7 electron volts. Okay, that means this band gap is very small in semiconductors. So if you give little amount of energy also, even room temperature also, what happened? So some valence electrons are going to the conduction band, so conduction will be takes place in case of semiconductors. Okay, now coming to the conductors. Means, so these valency band and conduction band both are overlapped with each other. There is no energy gap between the valency band and conduction band. Okay, so here no need to give any energy. There is a free electron will be there. In case of metals. That's why metals will act as a conductors. Okay, so now coming to, these are the based on the classification. So based on the classification of the material, so here by using band theory of solids, so we are classified the materials. Okay, so this is the band theory. Now coming to the semiconductor materials, we are discussing mainly on here semiconducting materials. Initially, intrinsic or pure semiconductors. Okay, so there are two types. One is the intrinsic or pure semiconductors. Another one is the extrinsic or impure semiconductors. Okay, so in case of extrinsic semiconductors, there are two types are there. One is the P type and another one is the N type semiconductors. First of all, we will discuss about the pure semiconductors. Okay, intrinsic semiconductors. In case of intrinsic semiconductors, so once again we will read here. A semiconductor which does not have any kind of impurities behave as a insulator at 0 Kelvin. Behave as a conductor at higher temperature is known as intrinsic semiconductor or pure semiconductor. Okay, so that is the definition of the pure semiconductor or intrinsic semiconductor. That means at 0 Kelvin it will be act as a insulator. At higher temperature it will act as a conductor. Okay, this is in case of semiconductors. Okay, now examples will be fourth group elements. Germanium and silicon are the best example for intrinsic semiconductor. Okay, so the structure will be diamond cubic structure. Okay, we will discuss how it will be. Okay, now so these materials have how many valence electrons? So intrinsic semiconductor, silicon and germanium. So there are 5 valency electrons will be there. So those 5 valency electrons are, that means each atom containing 5 valency electrons. So those atoms are covalent bond with the surrounding atoms. They can form a structure like a, so structure like a here. So finally diamond cubic structure we will get. Okay, so now here there are a, so if you will take each bonding, that is a tetrahedral structure. So if you will take total unit cell, so that is a diamond cubic structure. Okay, now coming to the, so today we will discuss about the, yeah, one more thing here. So briefly we will discuss about the semiconductors. Okay, yeah, so I will explain some properties of the semiconductors. So what are the properties of this intrinsic semiconductors? Intrinsic semiconductors, okay, they have resistivity, that means conductivity. Before that, what is the resistivity means? So inversely proportional to the conductivity, the resistivity less than the insulators, and what is that, more than the conductors. Resistivity will be less than the insulators, and so more than the conductors. That resistivity range is in between the conductors and insulators. Okay, now coming to the next property, the resistance of the semiconductor decreases with increasing the temperature and vice versa. Okay, suppose if you increase the temperature, of the semiconducting material, what happen means, so the resistance will be decreases, that means conductivity will be increases. In case of metals, how it will be? In case of metals, suppose if you will take metals at room temperature, its conductivity will be high. So if you increase the temperature, so what happens, that conductivity of metals will be decreases, but in case of semiconductor, that is opposite. If you increase the temperature, what happens, so conductivity will be increases in case of semiconductors. But metal, if you increase the temperature, the conductivity will be decreases, okay. Now coming to the, when suitable metallic impurities. So one more thing I have to discuss here. So in case of metals, so what I am discussing here, if you increase the temperature, what happens, conductivity will be decreases. If increasing the temperature, conductivity will be decreases. That means if you decrease the temperature, what happen, the conductivity will become so more. So like that, if you the temperature of the metals, we can decrease the absolute temperature up to lower temperature. If you going to the lower temperature, what happen, the conductivity of the metals will be increases, with decreasing the temperature. So at a particular temperature, those conductivity of the metals will become infinite. There is no resistance, at a particular temperature. If you decreasing the temperature, conductivity of the metals will be increases, at a particular temperature. What happen, so those conductivity will become infinite. At that temperature, those material will act as a superconductors. Okay, so at which the temperature, those material will act as a superconductor, that is transition temperature we will call it as. So that means, so based on this superconducting phenomena, so many techniques are developed. Okay, so many techniques are developed, we will discuss that in so while yeah, third unit we will discuss about this. Third or fourth unit we will discuss about these superconductors. Okay, so then we will discuss about the third property of the intrinsic semiconductor. So what is that means, when a suitable metallic impurity is added to a semiconductor, its current its current conducting properties increases. Okay, so that means if you will take doping, if you will add any doping element into the semiconductor, what happens, its conductivity will be increases, here. Okay, now coming to the, so briefly discuss about again semiconductor here. So there are some examples of pure semiconductors. So what are those examples mean, germanium and silicon. So here definition again, a semiconductor in extremely pure form is known as intrinsic semiconductor. Already previously I gave one definition, that also you can write. Okay, so here pure semiconductor examples are germanium and silicon. Okay, so now how current passing through this intrinsic semiconductor we will discuss here. So in case of intrinsic semiconductor, so number of electrons in a conduction band equal to the number of holes in a valency band. Number of electrons in a conduction band is equal to the number of holes in a valency band. Okay, so that means both are equal. Both are equal in case of intrinsic semiconductor. In intrinsic semiconductor, now we will apply the positive terminal to the one side and negative terminal to the one side of pure semiconductor. What happened here? So this is the negative terminal. Yes, negative terminal is applied here. So because of negative terminal, what happened? So electrons are repelled by the negative terminal. So that's why electrons move like this direction. Electrons will move like this direction. Okay, and so positive terminal is connected to the this terminal here. So okay, so that means what happened here? Because of the positive terminal connection, holes are repelled by this positive terminal. Okay, so holes will move this direction. So electrons will move like this direction, holes will move like this direction. Okay, so now, so electrons are moving like this. Okay, like this. Okay, so what happened? Holes. So due to electrons only, here conduction will be takes place. So due to the motion of the electrons, so conduction will be takes place. What happened to holes means, so these electrons so complete the circuit. Okay, again coming like this direction here in this region. That means if you will take B region, if you will take, so in this B terminal, what happened? So recombine with the, again recombine with the electrons. These holes are recombined with the electrons. Okay, so that means here due to the these negative terminal, electrons are repelled like this direction, so it will move like this direction, and so current passing through the circuit, current passing through the circuit. Okay, so now, so after completion of the circuit, what happened means, so after completion of the one circle, so these electrons again recombine with the holes, recombine with the holes at the terminal of B. Okay, because holes are attracted by the, so this side, so that's why here holes are recombined, holes are recombined. Okay, like this in case of semiconductor, current is passing, like this in case of semiconductor, current is passing here. Okay, now coming to the yeah, so extrinsic semiconductors we will discuss. Okay, uh, at room temperature, intrinsic semiconductor has little current capability. So that means if you will take room temperature, intrinsic semiconductors have very less charge carriers in conduction band. Okay, so that if you want more current at room temperature means we have that what is that, the pure semiconductors are not suitable. If you want, so very high current, if you want very high current at room temperature means, so the intrinsic semiconductors are not suitable. So that's why, so what we will do means, so already we studied one property. What happen if you dope any material into the extrinsic semiconductor, what happen, its conductivity will be changes, its conductivity will be changes. Okay, so based on that property, so what we are doing means, in our, so we are doping some material. So if you want to use high what is that, high conducting properties, so we need high conductivity at room temperature. For that's why, for increasing the conductivity of material, what we are doing means, yeah, so we are doping with some material, we are doping with some material. Okay, yeah, once again read, I will read here. So the electrical conductivity of the intrinsic semiconductor can be increased by adding some impurities in the process of crystallization. Okay, so when we will add the means, so while preparing the semiconducting material, when we will dope this means, so in the crystallization process, that means what is the crystallization process means, so while preparing the semiconducting material, while preparing the semiconducting material, we will dope here. Okay, so the added impurities is very small. So the impurities we are doping means, we are doping some elements. Doping is nothing but adding impurities is called as doping. Adding impurities we called as doping. So that doping is very small. How much is small means, so one atom per million atoms. Suppose if you will take silicon. Okay, so in that silicon, just one atom, so for 1,000 silicon atoms, for 1000 silicon, million silicon atoms, so we are doping just one impurity atom. So that impurity atom also very small. Okay, so such semiconductors we will call it as impure or extrinsic semiconductors. Such semiconductors we will call it as impure or extrinsic semiconductor. Okay, now so what is the doping definition? What is the definition of doping? The process of adding impurities to a semiconductor is known as doping. Okay, the process of adding impurities to the semiconductor is known as doping. Okay, that means in the doping we will add very small impurities for for million atoms, million pure semiconducting atoms. Will dope only one impurity atom. Okay, so the doping concentration is very small. Okay, now coming to the here, there are two types of doping material will be there. We will use. So what are those doping material means? So pentavalent atoms or trivalent atoms. What is the example for pentavalent atoms means? Arsenic, antimony, bismuth. Okay, so arsenic, that means bismuth here, antimony, arsenic, phosphorus. So these are the pentavalent atoms. These are the pentavalent atoms. So and trivalent atoms. What are the trivalent atoms? Here gallium, aluminium, indium, and boron. So boron, gallium, aluminium, indium. So these are the trivalent atoms. Trivalent atoms. Okay. Now, so what happens if you dope the pentavalent atoms? What happens if you dope the pentavalent atoms? We will discuss. The pentavalent doping atom is known as donor atom. Donor atom. So pentavalent means its outermost shell there are 5 valency electrons will be there. So if you will take pentavalent means there are 5 valency electrons will be there in the outermost cell. Outermost cell. So that's why what happened? It will suppose if you will take silicon or germanium, there are only 4 valency electrons will be there in the outermost cell. Okay. So if you use pentavalent means it donates the electrons. It donates the electrons. Okay, so that's why we will call it as, these are the pentavalent elements, we will call it as donor atoms. Okay, so these electrons involved in a conduction process. These electrons involved in a conduction process. These pentavalent atoms donate electrons. These electrons involved in a conduction process. Okay, so that's why these pentavalent atoms we will call it as donor atoms. Donor atoms. Next one is the trivalent atom. And trivalent atom is also called as acceptor atom. Trivalent atom is called as acceptor atom because it accepts one electron from semiconductor atom. Okay, so that means trivalent atoms having only 3 electrons in outermost cell. Trivalent atom having only 3 electrons in outermost cell. So that's why what happened. So that if you will dope the trivalent atom, so but the germanium, if you will take either germanium or silicon having 4 valency electrons, so only 3 trivalent have only 3 electrons in outermost cell. So that's why, so 3 germanium atoms are bonding with these trivalent atom. So that one more that here, but germanium required, either germanium or silicon required. So one more electron. So this does not supply the, so one more electron. So that's why, so it accepts the electron. Trivalent atom accepts the electron. Okay, that's why. So these are the acceptor atom. So we will call it as, it is the acceptor atom. Okay, now coming to the, depending on the type of impurity added. Depending on the type of impurity added, the extrinsic semiconductors can be divided into two types. So one is the N-type semiconductor, another one is a P-type semiconductor. Depends on the doping type, which type of doping element we are using, which type of doping atom we are using. So depends on the doping atom. So extrinsic semiconductors are divided into two types, two categories. So one is the N-type semiconductor, another one is the P-type semiconductor. Okay, now coming to the N-type semiconductor. So N-type here, so N-type extrinsic semiconductor. Okay, now, so what is the N-type extrinsic semiconductor? So when a small amount of pentavalent impurities added to the pure semiconductor, semiconductor crystal during the crystal growth, or so what is that manufacturing process, okay, so crystallization process, anything, okay. The resulting crystal is called as n-type extrinsic semiconductor. N-type extrinsic semiconductor. Okay. See here, if you will take what is the phosphorus we are doping here. Phosphorus we are doping. So in case of germanium atom, in case of that means for million germanium atoms, so we are doping. So one phosphorus atom here. So that phosphorus atoms bonding with the surrounding germanium atoms. That phosphorus atom is surrounding that bonding with the surrounding germanium atoms. That bonding also covalent bonding. That covalent bonding. Okay. See here. So that means here germanium requires so 4 electrons. Germanium requires 4 electrons to get the to fulfill the what is that uh, bonding, to fulfill the bonding. So here germanium requires 4 electrons, but here phosphorus outermost electron only, so 5 electrons will be there, 5 electrons will be there. So that's why what happened, so here so 4 phosphorus electrons, 4 phosphorus electrons are bonding with so 4 germanium atoms, surrounding germanium atoms. There is a one phosphorus electrons will be free. So this electron not involved in a this electron not involved in a bonding. So this electron not involved in a bonding. So that's why. So what is that attraction between this phosphorus atom and this electron will be very small, very small. If you give very little amount of energy also, what happen? It will become free. It will become free, and so this electron will jump very easily to the conduction band, very easily to the conduction band. If you give, because so what is that interaction between attraction between this phosphorus nucleus and this electron will be very small, very small. That's why if you give the little amount also, what happen, this electron will jump to the conduction band, it will move, this electron will move freely, so entire the atom, entire the atom. Okay, so that's why. So what happened, each phosphorus atom donates one free electron, each phosphorus atom donates one free electron, because so phosphorus have so 5 valency electrons. So in that 4 valency electrons are bond with the surrounding germanium atoms. There is a one excess electrons will be there, that excess electron have so very less bonding with the phosphorus nucleus. That's why if you give very little amount of energy also, so what happen, it will goes to the conduction band. If you will take silicon, if you give 0.01 electron volts, if you give 0.01 electron volts energy, so what happen, this electron will goes to the conduction band, this electron will goes to the conduction band. If you will take germanium atom, if you will take germanium atom, if you will give just 0.05 electron volts, if you give 0.05 electron volts, so what happens, this electron will goes to the conduction band. Okay, so that means so very less amount is required, this electron will goes to the conduction band. Okay, that's why. So what happened in case of n-type semiconductor, there are so many number of free electrons will be there, so many number of free electrons will be there. Okay, so now once again I will revise through matter. Consider the case when the pentavalent p atom is added to pure germanium crystal. The p atom fits, so phosphorus atom fits in the germanium crystal. Phosphorus atom fits in the germanium crystal in such a way, that its 4 valency electrons from covalent bond with the 4 germanium atoms. The 5th electron of phosphorus atom is not covalent bonded, so but it is loosely bound to the parent atom, parent phosphorus atom. Okay, so this electron is available as a carrier of current, carrier of current. Okay, now the amount of energy needed to detach this 5th valency electron from impurity atom is the order of only 0.01 electron volt for germanium and 0.05 electron volt for silicon. Okay, the past using phosphorus impurity here. Okay, so previously we discussed this energy is very small and provided with the thermal excitation at room temperature. Such liberated valency electrons then free to move in the crystal lattice. Okay, although each p atom provides only one free electron. At an extremely small amount of p impurity provides enough atoms to supply the millions of free electrons. Okay, see here. Okay, am I audible?
Yes.
Students? Okay,
Yes.
yeah. So due to some network problem, again it was disconnected. Yeah, we will go for this. Mm. Yes, so here we are adding the phosphorus atoms. So 4 electrons are, that means 4 electrons of phosphorus atoms are involving in a covalent bond. So there is a one free electron will be there. Okay, so if you add the, so that means each phosphorus atoms will providing so one free electron. Okay, so that means free electron is nothing but this is a little bond with the phosphorus atom. That bonding energy also very small. If you give very little amount of, that means at room temperature also it will escape from the phosphorus atom. So that's why what happen, if it will be released from the this phosphorus nucleus, that means it will free and it will move entirely, so in entire crystal or entire material. Okay, so this electron will move so through entire material. That means that this electron we will call it as free electron. This so this electron involves in a conduction process. Okay, so here we are adding very little amount of impurity also. There are millions of phosphorus atoms are added, okay, so that's why, so there is millions of free electrons will be present, in case of what is that, n-type intrinsic semiconductor, n-type intrinsic semiconductor. So that's why here compared to the holes, so in case of intrinsic semiconductor, so electrons are very high. Okay, so that means holes also present here. How holes are present means, so if you give the energy, so high energy, that means energy, so we will supply the some energy, means what happen, so these bonded electrons also escape from the valency band. Okay, so that's why what happened, holes will be present in valency band, so in conduction band, so including this bonded electron, there are free electrons also there, so that's why in case of n-type semiconductor, majority charge carriers are the what is that, electrons. Majority charge carriers are the electrons, minority charge carriers are the holes, so compared to the holes, electrons are very greater. So compared to the holes, in case of n-type semiconductors, holes will be very less. So compared to the holes number, so electrons number is very high. Electrons number in conduction band is very high. Okay, so now I'll go the, so properties, so sorry, some important points in case of n-type semiconductor. Okay, in n-type semiconductor, the electrons are majority charge carriers, while positive holes are the minority charge carriers. Okay, this second point is not required for you. Okay, so now coming to the, so finally what we have to conclude means, in case of n-type semiconductor, so majority charge carriers are electrons, minority charge carriers are holes. So compared to the holes number, so electrons number is very high. Electrons number in conduction band is very high. Okay, so that is the conclusion, final conclusion in case of intrinsic n-type semiconductor. Now p-type extrinsic semiconductor. P-type extrinsic semiconductor. Okay, now coming to the, so definition. When a small amount of trivalent impurity is added to the pure crystal during the crystal growth, the result crystal is called as p-type extrinsic semiconductor. P-type extrinsic semiconductor. So what we are doing means, so we are adding the trivalent impurity atom while preparing the that is that extrinsic semiconductor. While preparation of, so semiconductors, we are adding here, so trivalent impurity atom. So what are the example of trivalent impurity atom? Allium, indium, so gallium, aluminum, indium, and boron. Okay, so these are the trivalent atoms. Examples of the trivalent atoms. So these trivalent atoms having, so three valency electrons. Okay, so if you dope the trivalent atom into pure intrinsic semiconductor. So what happened? So it will covalent bond with the surrounding germanium atoms. It will covalent bond with the surrounding germanium atoms. Okay, so but boron have only 3 valency electrons. That's why it's covalent bond with the only 3 germanium atoms. Only 3 germanium atoms. Okay, so for but germanium require 4 valency electrons. Germanium require 4 valency electrons. So that's why one electron deficiency will be present. One electron deficiency will be present while bonding. Okay, so that's why. So here there is a deficiency will be there. Electron deficiency will be there. So that we will consider as a hole. Electron deficiency will be there for bonding with the germanium atom. So that electron deficiency is we will consider as a hole. Okay, now coming to the so once again I will read here. Consider the case when trivalent boron is added to the pure germanium crystal. Each atom of boron fits into the germanium crystal with only 3 covalent bonds. This is because the 3 valency electron of boron atom from covalent bonds with the valency electron of germanium atom. Okay, see here. So that means if you will take the boron, so boron provides electrons. That's why. So those 3 electrons only bond with the surrounding 3 germanium atoms. Okay. In the fourth covalent bond, fourth covalent bond, only germanium atom contributes. Only germanium atom contributes 1 valency electron, and there is no deficiency of the 1 electron, which is called a hole. Okay, so that means here 3 covalent bonds occurring between the germanium and boron, and for fourth covalent bond, what happened? So only germanium provides the electron. So that means there is no electron for boron. So that's why. So there is a deficiency of electrons here. That deficiency of electron we will consider as a hole. Okay. Now coming to the, in other words, we can say that the fourth bond is incomplete, being short of 1 electron. Okay, here fourth bond is incomplete, short of 1 electron. Therefore, for each boron atom added, 1 hole is created. A small amount of boron provides million of holes. Okay, if you dope the small amount of boron also, here there are so many, that means each boron atom provide 1 hole here. Okay, that's why if you small amount, if you add the very small, that means a 0.1% also, it will provide millions of holes. Okay, so now coming to the so the addition of trivalent impurity produces a large number of holes in the valency band. Okay, these these holes will be present in the valency band only. Okay, however, there are few conduction band electrons due to thermal energy associated with the room temperature. Okay, so what we discussed, if you give the little amount of the energy also, what happen? Those covalent bond will breaks, and so those electrons will goes to the conduction band. That means at room temperature also what happen? So some electrons will be present in conduction band. Some electrons will be present in conduction band. That means so compared to the holes, see here. So already, so due to the what is the doping of the boron, there are some holes will be there. So if you give some energy, what happens? These electrons will escape and will move to the conduction band. So that's why compared to these conduction band electrons, what happen? So holes will be very high. Holes will be very high. Okay, so that means so in case of p-type extrinsic semiconductor, number of holes is greater than the number of holes in valency band is greater than the number of holes electrons in conduction band. Okay, so in case of p-type semiconductors, number of holes in valency band is greater than the number of electrons in a conduction band. So that means in conduction band, number of electrons are very small compared to the holes. That's why majority charge carriers in p-type semiconductors are holes. Minority charge carriers in p-type semiconductors are majority charge carriers are holes. Minority charge carriers are electrons. Minority charge carriers are electrons. Okay. Sometimes we can neglect also. Sometimes So these minority charge carriers we can neglect. Similarly, in case of n-type semiconductors also, minority charge carriers we can neglect. That's because these majority charge carriers value will be very high compared to the minority charge carriers. Okay, now how conduction will be takes place? So here, so in valency band, so there is very little amount of electrons will be there. So how conduction will be takes place? Due to the holes. Due to the holes we will discuss here. Okay, so now, so in the complete covalent bond, yeah, 1 minute here. Here, the addition of trivalent impurity process a large number of holes in the valency band. However, there are few conduction band electrons due to the thermal energy associated with the room temperature. Okay, this already we discussed. Okay, now coming to the next point, the complete covalent bond, the remaining fourth electron of germanium atom also tried from a covalent bond. Okay, so here that means germanium electron, only 3 germanium atoms are covalent bond with the boron atom. One germanium atom is not bonded. Okay, so that germanium atom also try to covalent bond with the boron atoms. What happened means, so that's why it steals an electron from the neighboring germanium atom. It steals electron from the neighboring germanium atom. Okay, so that's why what happened is that means one germanium atom is not completed the covalent bond. So that's why what happened, it tries to become a covalent bond. It tries to become a covalent bond. So that means if you want, that means if germanium fulfill the covalent bond means it steals the sum, it requires the sum electron. How it will get the electron means it steals an electron from the neighboring germanium atom. Due to this stealing action, stealing means so forcefully taking electron from the surrounding atoms. Stealing is nothing but forcefully taking electron from the surrounding atoms. Okay, so due to this stealing action, hole is created in the adjacent atom. This process continues and holes will move about in a random way due to thermal effects. Okay, impurity atoms that contribute holes in this manner are termed as acceptor because of they accept electrons from the germanium atoms. Since current carries accept electrons from germanium atoms. Okay, 1 minute. Since current carries are positively charged particles, holes only, this type of semiconductors is called as P-type semiconductors. Yeah, I will explain you here once again. So here that means here germanium atom is not fulfilled covalent bond. So same structure will be surrounding will also there. Okay, so what happened here? This germanium atom try to capture the electron from the surrounding germanium atom. Suppose so this germanium atom capture this electron. So this germanium atom capture this germanium atom electron. What happened? Here hole will be present. And similarly here also some another nearer germanium atom will be there. So that germanium this germanium atom now steal the electrons from surrounding germanium atom. Like that, what happened? Holes will move from one place to another place. Holes will move from one place to another place because this electron will jump from here to here. Okay, here hole will be formed. So this germanium atom again try to complete the covalent bond. That's why it's still from the electron from surrounding germanium atom. That's why another germanium, it's still the electron from another germanium atom. So that's why it's still the electron. So that's why here hole will be occur. So this process will be continuous. So that's why what happened? So holes will move inside the material. So due to the motion of the holes, here conduction will be takes place. Due to the motion of the holes, what happened here? Conduction will be takes place in case of P-type semiconductors. Okay, understood? There are so many number of holes will be there. Now we are just discussing about the one hole. So if you add some little amount of impurity atom also, so there are so many holes will be present. Those all holes So that means that all holes in the all hole structure so behave like that only. Okay, so behave like that only. All holes will move from one place to another place. Okay, so that's why what happened. So due to these holes, conduction will be takes place in case of p-type semiconductors. P-type semiconductors. Okay, so that's why here p-type semiconductors are majority charge carriers. Majority charge carriers due to p-type semiconductor. What is that? In case of p-type semiconductor, due to holes only current is passing. Current is passing. Okay, so here electrons are very small amount. That's why. So due to holes only here, current is passing inside the p-type extrinsic semiconductors. Okay. Now coming to the so what are the majority charge carriers in p-type semiconductor? Holes are the majority charge carriers, and what are the minority charge carriers? Electrons are the minority charge carriers. Okay. Now, so we'll read the some important points. So what is that important point means? In p-type semiconductor conductor materials, the majority charge carriers are positive holes, while not so minority charge carriers are electrons. Okay. Now second point is it is electrically neutral because the number of mobile holes under all conditions remain equal to the number of acceptor atoms. So that's why. So this is what is that electrically neutral. So this is about the so p-type and n-type semiconductors. This is about the p-type and n-type semiconductors. Okay. Now now we will discuss about the so that is the so p-type and n-type semiconductors. Okay, now we will discuss about the so intrinsic semiconductor. In case of intrinsic semiconductors, so what is the charge carriers? Holes and electrons. Okay, so we have to find out the carrier concentration of intrinsic semiconductor. Carrier concentration of intrinsic semiconductors we have to calculate here. Okay, so in case of intrinsic semiconductor, what are the charge carriers here? So both electrons and holes are the charge carriers. Electrons and holes are the charge carriers. Okay, in case of intrinsic semiconductor, number of electrons in a conduction band is equal to the number of holes in a valency band. Okay, so that means we are calculating the how many electrons will be present, how many holes will be present, we will calculate here. Okay, so for that, so just consider here. So electrons will be present in conduction band, holes will be present in valency band. Okay, here we know that yesterday we discussed that the kinetic energy of the electron. What is the kinetic energy of the electron means? Depends on the position. So it will those will get the potential energy. So here, so those are in conduction band. So that is the conduction band is position. That's why. So conduction band is act as a what is that potential energy. So total energy is E here. So kinetic energy of the electron equal to E minus EC. E minus EC. Similarly, so kinetic energy of the hole equal to EV. EV is the valency band. Valency band. So position. Yes, is it visible? Students?
Yes, sir.
Okay. Yeah. So now we are discussing about the carrier concentration. Carrier concentration in case of intrinsic semiconductor. So just now, up to now, we are discussing just about the introduction of the semiconductors. How many types? So what is the pure, impure semiconductors? Types of semiconductors we discussed. So main here. So what is the topic? Main topic is started from here onwards. Okay. So now, so carrier concentration of intrinsic semiconductors. So first of all, so in case of intrinsic semiconductor, so what are the charge carriers means electrons and holes, both are the charge carriers here. Both are the charge carriers. Okay, so that's so number of electrons in a conduction band equal to the number of holes in a valency band. Okay, now coming to the so first of all, before going to the calculation of the charge carrier concentration, we have to know what is the kinetic energy. What's the kinetic energy of the electron? What's the kinetic energy of the electron means? So here E is the total energy of the electron. So now kinetic energy of the electron equal to E minus EC, because EC is the conduction band. So that means what is that energy of the conduction band? This gives the position for the electron. That's why depends on that position we can measure that. That is a what is that? So potential energy. Okay, so now kinetic energy equal E minus EC. So suppose if you will take this electron, so what is the kinetic energy? E minus EC, E minus EC. So in that this is the total conduction band. So total conduction band minimum energy level is EC. Conduction band minimum energy level is EC. So what is the maximum energy level? We don't know. We don't know. That is the infinite. So minimum energy level of conduction band is EC. Maximum energy level of conduction band is infinite. Similarly, so maximum energy level of valency band. Maximum energy level of valency band is EV. Okay. So and so what is the minimum level? Minimum energy level. Minimum energy level is we don't know that. Okay. That's why we are taking minus infinity. Minus infinity. Okay. So minimum energy level of valency band is minus infinity. Maximum energy level of valency band is EV. Okay. Now, so minimum level of conduction band is EC. Maximum energy level of conduction band is infinity. Okay. Now EF is the Fermi level. EF is the Fermi level. What is the Fermi level means? So in case of definition of the Fermi level is, so maximum energy level of the electrons, maximum energy level of the electrons at absolute temperature. Maximum energy level of the electrons at absolute temperature is called as Fermi energy level. Fermi energy level. That means absolute temperature is nothing but 0 kelvins. 0 kelvins. So if you will take 0 kelvin, so the energy of the electrons will be so less than this Fermi level only. Less than this Fermi level only. That means there is no electrons. There is no electrons in conduction band. There is no electrons in conduction band. That means above the Fermi level. Above the Fermi level at 0 kelvins. At 0 kelvins. Okay. So if you will take pure semiconductor, the Fermi level will be in between the what is that conduction band and valency band. Conduction band and valency band. If you will take pure means it will be middle. If you will take pure semiconductor means that the Fermi level will be middle. Okay. If you will take impure means that Fermi level will be changes. Fermi level will be changes. Okay. We'll discuss about the Fermi level later. Okay. Now first we are going to the here. For finding the first we will calculate the density of electrons. So if you want to calculate the carrier concentration of the intrinsic semiconductors means what we have to do means first of all we have to find the density of electrons. Okay, so then we have to find the density of holes. Okay, so that means here so total, so density of electrons plus density of holes, it will give the so carrier concentration in case of intrinsic semiconductors. That's why first of all we have to calculate the density of electrons. Okay, let us take, so density of electrons is nothing but, so what is the density of electrons means, so in case of pure semiconductor, density of electrons means in case of conduction band how many number of electrons will be present, how many number of energy states or electrons will be present, we have to calculate here. How many number of electrons will be present, so we have to calculate, so that is the density of the electron. Okay, for that let dn be the number of electrons per unit volume, number of electrons per unit volume. So what is the density, how we will calculate, so number of electrons per unit volume. Okay, here dn, so dn be the number of electrons per unit volume in the range, in the energy interval, E and E plus dE, Okay, so if you will take dn equal to E and E plus dE, so total energy density of the electrons, in that what is that energy interval E and E plus dE is equal to dn. Okay, so dn is equal to, so what is the formula means ZE dE into F of E. So what is the ZE dE? Okay, ZE is the density of states in the energy interval E and E plus dE. Okay, then density of the states. Okay, so here, so suppose if you will take conduction band, so many number of energy states will be there. See here, once again. So if you will take conduction band here, so there are conduction band will be combination of number of energy states, already we discussed. Okay, so we are taking here So some energy range E and E plus D range. In that E plus D range, so many number of density states will be there. Okay, so many number of density states will be there. Those density states are ZEDE. Those density states are ZEDE. So in that density states, how many electrons will be present in the density states means, so F of E. F of E is the probability of finding the electron. Probability of finding the electron. So this is the, by using Fermi-Dirac distribution function, we are calculating the probability of the electron here. Okay, so here F of E is the probability of finding the electron in the, what is that? Those density states. Those density states. That means total number of electrons is equal to, so energy density states into probability of the finding the electron. So number of electrons is equal, Dn is equal to Z of E dE into F of E. Z of E dE is equal to density of the states. Density of the states, and F of E is the probability of finding the particle. If you multiply both means we can get the number of electrons in the energy interval. In the energy interval E plus E to E plus dE in this energy interval. So how many electrons will be there means Dn electrons. How to calculate Dn means Z of E dE into F of E. Okay. So now if you want total number of electrons, total number of electrons means we have to integrate from lower limit to upper limit. So what is the lower limit of conduction band? EC. So upper limit of conduction band infinite. Okay, so that's why if you want to calculate the total number of electrons, N is equal to so integration of EC to infinite into Z of E F of E dE. Z of E F of E dE. This gives the total number of electrons. Okay, now so density of the states. So the density of the states. Okay, so in the interval E and E plus dE. Okay, that is Z of E dE. So this calculation is not required for you. So density of states. So you have to remember this. You have to by heart this. Okay, the density of states Z of E dE. Z of E dE is equal to 4 pi by h cube into 2m whole power 3 by 2 into e power 1 by 2 dE. Here E means effective, what is that energy of the electron or kinetic energy of the electron. Okay, effective energy of the electron or kinetic energy of the electron. Okay, so here density of state Z of E dE is equal to, so this value, you have to remember this value. You have to by heart this value. Okay, so this calculation is not required for you. Okay, that's why, so I will not tell you this calculation. So you have to by heart this equation. So this is the density of the states in the energy interval E and E plus dE. Okay, now applying this formula for electron in conduction band, okay, instead of E, what we are taking here, so effective energy of the electron, because so here due to the position what happened, so those will get some potential energy. So that means if you want effective energy means, so you will get E minus EC, that is the kinetic energy of the electron, instead of E we are substituting here E minus EC. Okay, previously we discussed here. Okay, so E minus EC, that is the kinetic energy. So total energy is equal to, so kinetic energy plus potential energy. Here potential energy equal to EC. So now kinetic energy equal to E minus EC. Okay, so that is that about the, yeah. So now, so we are substituting the effective energy of the electron and mass of the electron. Here my mass also we are taking. So effective mass of the electron, Me is the effective mass of the electron. Okay, just we are substituting effective energy of the electron and effective mass of the electron. This is the density of the states. Now coming to the, we have to find out the probability of finding the electron. So for probability of finding the electron, we are using here Fermi-Dirac equation, Fermi-Dirac distribution function. Okay, so but in Max Planck we are discussing about the, so Maxwell distribution function. Okay, so but for electrons here, so for explaining the electrons, we are taking here Fermi-Dirac distribution function. So what is that Fermi-Dirac distribution function means? F of E is equal to 1 by 1 plus exponential of E minus EF by KT. So this is the Fermi-Dirac distribution function. By using this function, we can calculate the probability of finding the electron. In a energy states. states. Okay, now here, so we will simplify this equation. So E minus F. E minus F means energy of the electron. Energy of the electron. Okay. So that energy. So, yeah. So that means E is the energy of the electron. F is the Fermi energy. Fermi energy. Okay. So difference between these two. Difference between those two is very high. Very high. So compared to the thermal energy. So that means E minus Ef is in case of N types, in case of pure semiconductors. So if we are taking the conduction band here, so that's why, so E minus Ef value is very, very greater than the, so thermal energy. So that's why what we are doing means, so this value also, E minus Ef value is very greater. So that's why what happened, exponential value also very high. Exponential value also very high. That's why we can neglect the one here. We can neglect the one value. So that because this value is very, very high, very, very high. So that's why, so we can neglect this one value. So finally this equation will become f of e is equal to, so 1 by exponential of e minus ef by kt. Okay, so now if you simplify this equation, so bring this equation into, so like this. So if you will come into the numerator, so numerator it will become minus. So if you simplify it, so if you will take minus common, so it will become exponential of ef minus e by kt. So this is the f of e value. This is the probability of finding the particle. So now coming to the, so n, so total number of electrons. So how to find means, so we have to integrate the, so this dense, so dn value, we have to integrate the dn value. So dn value equal to z of e f of e into de. So substitute the z of e and de value and of f of e value. Okay, so z of e de value is equal to 4 pi h cube into 2me whole power 3 by 2 into e minus ec whole power 1 by 2, and f of e value is equal to exponential of ef minus e by kt into te. So this is the, so total number of electrons will present in the conduction band. So what is the lower limit? Ec. Upper limit? Infinite. Okay, now simplify this equation. So what is the constant? Bring outside. Okay, so 4 pi by h cube is constant and 2me is the constant. So that's why I bring outside here. Now, so e minus ec whole power 1 by 2 into, so what, for simplification, what I am doing means, so I am adding and subtracting. With ec. Okay, so that's why, so only variable is here e. Is the variable. Remaining all values are constant. E means energy of the electron. So for different electrons, the energy will be different. Okay, so that means here Fermi level is constant. Okay, and what is that? EC. EC means so minimum energy of the conduction band. That also constant. Only E. E is the energy of the electron. That energy of the electron only varies. Okay, different electrons having different energies, because we are taking here, so so many number of, from what is the range, from so EC to infinite.